Aliki Loper-Ledy, and I will be taking you through the Uranus probe system, or the UPS vehicle here, for the mission architecture. Slide, please. Here we have the basic requirements of what UPS will be doing. Essentially, UPS will be delivering the first and second probe to Uranus. That probe will do its data collection, and then the UPS itself will send back that data to the probe. Next slide, please. Here's a basic overview of some of the things UPS will be doing. We do have a dual launch manifest, so we'll have two UPS vehicles inside the launch vehicle side by side. We have designed our own specialized payload attachment for that purpose, which will be discussed later in the structural analysis section. We're also a spin stabilized spacecraft because we'd like to make the spacecraft a little bit more simple. The point is to just be essentially a bus which takes the probe to Uranus. It will not have any scientific measurements or instruments on board to do that work, just transferring data. As far as our communication system, we have a high gain antenna which will be in charge of doing all communications back to Earth in transit and after its Uranus flyby to transmit the probe data back. And we have a medium gain helix antenna which will be receiving data from the probe, storing it on board, and then sending it back with that high gain antenna. Slide, please. Here we have our mass breakdown of the UPS. Essentially, we have an allowable mass of 431.5 kilograms with 31.5 kilograms of contingency. And just like the orbiter, it's structured the same way. So we have our best estimate from subsystems, the margin on top of that given by each subsystem of what they believe is best for their system. And then the design mass and allocation, since we worked with the same system of having allocated masses and making subsystems try and fit that allocation. If not, they would trade and try and figure out their masses that way. Slide, please. For our power budget, we have nominal power for all the hardware shown here, adding up to about 100 watts for UPS. The important thing to see here is that our ASRG at end of life is about 112 watts. So we do technically close for UPS with only one ASRG. Unlike the orbiter, which has 3, so we don't necessarily have that redundant ASRG, but we do believe that our power system will close this way. Slide, please. For our pointing budget, we have 2 things that we're concerned about for our communication in our probe, with a pointing requirement of 0.2. The communication system includes the high gain antenna and needs to be pointed accurately during its transit for housekeeping with the high gain antenna, and also after Uranus to send back that data over time. The probe accuracy is actually the spacecraft itself, because when UPS comes into the Uranus sphere of influence, we need to have the spacecraft pointed accurately to make sure that when we drop our probe, the probe is entering into its correct trajectory into Uranus. Slide, please. For our data budget, as you can see here, our CDH system is 480 NIPS, but we're actually only using 78.8 of that amount, which means we can reduce our power for that system since we won't be using all of our capability at that point.
I'm sorry, I have one quick.
Yes.
That previous slide, the pointing of the spacecraft. So you're saying that to induce the probe trajectory, you have a 0.2 pointing requirement. But once you release the probe, the UPS is going to do continuous communication back to Earth while it's going through its orbit, right?
Yes, essentially UPS will be, and we'll get into this, but UPS will be coming in, it will orient to drop the probe, it will immediately do a burn to get onto a flyby trajectory around Uranus, in which it will be receiving data from the probe around Uranus. After it takes its flyby, it will then reorient the high gain back to Earth and do transmits.
And then while it's in that high flyby orbit, it can maintain that 0.2 pointing accuracy.
I would have to direct that to the comms or ACS team.
It's only a 4-degree point accuracy. We actually designed the probe receive helical antenna. It's on the UPS to have a beam width wide enough to cover 2 Uranuses at the orbital distance it will be at. So as long as it's pointed in the general direction, it should be fine.
Cool.
Yeah, it's 15 degrees or so.
Slide, please. Alright, so here we have our delta V budget. Like I mentioned before, we have essentially we have 2 burns in UPS. So UPS will be on the launch vehicle, and then once they separate, they'll do all their orientation checks, and each UPS will take their own delta V of around 150 meters per second in opposite directions of each other to put them on their separate paths to Uranus, since they are separated by the 2.5-year period to make sure that those probes meet the RFP and do their separate, arrive at their separate times. The other burn we do in UPS is to separate from the probe, like I mentioned a few minutes ago, that the UPS needs to not go on an entry trajectory with the probe, so we do a slight burn there to get around Uranus. Slide, please. All right, so here you can see our trajectory options. UPS has several more options than the orbiter as far as what we can do. So we have multiple launch windows. The one we chose is the bottom bolded one, with UPS 1 launching for 13.6 years and UPS 2 launching for 16, or it will be going for 16.1 years. We also will be launching on March 28, 2020, which meets the RFP requirement, since, as you now know, the UPS will be launching first before the orbiter.
I'm going to harp on your guys' significant digits again. 0.22705. Just saying. I think you guys need to look at the numbers and see if you actually have that accuracy. And if you don't, or if you do, fantastic. But I think you need to round those.
Also, it should be consistent. If you have one value at 5 digits, they should all be 5 digits, or one at 3 digits, they should all be.
But the first comment is actually more accurate.
Yeah.
Nobody has that kind of accuracy.
Actually, if you guys have that kind of accuracy, could you tell us in the street how you did it?
Yeah.
Okay, so we'll move on to the next slide with our portrait plot of the UPS trajectory. Similar to what you saw at the orbiter, except for it doesn't have those multiple flybys. Essentially, you can see in the bottom axis with the departure date, it's a more sensitive area. If you were to move a week over, you're going to change a lot in the delta V pattern versus a year. And so from this graph, we were able to develop, it was involved in developing our launch window of 20 days for UPS, which includes a unpowered flyby at Jupiter. Slide, please. Here's a graph of our launch window. As long as the black line, which represents our UPS wet mass, is below the red allowable launch mass, we have our launch window. This is the launch window we have chosen, but UPS has 2. So if this graph were to continue, you would see the other one that is our option for UPS. The other launch window is 1 year later from this point, if something were to happen in our mission. Slide. Just a little overview. We will be launching from Kennedy Space Center with a C3 of 83.4 on March 28th, 2020, with our launch window of 20 days from March 19th to April 8th on the Delta IV Heavy launch vehicle. Slide, please. Okay. So a little bit about the concepts of UPS. Essentially, UPS is in the launch vehicle next to each other, dual manifest, and then one will separate before the other. We did have a concern that if we separated them both at the same time, they might hit each other or something could happen, so we wanted to stagger their separation just for reliability. And so they're 30 minutes apart from each other, and then once they're both separated, we'll pressurize our tanks. We will have 3-axis stabilization at that point and orient our star trackers away from the sun. Then we will be able to have our communications, and once that's all set up, then we will do that first burn that I mentioned before of 157 minutes. At that point, we'll be ready to reorient our high gain antenna at Earth, since which will get a little bit into the configuration of UPS later, but essentially our more powerful thrusters on the opposite side of the high gain, so we have to rotate the spacecraft back around after doing that burn to get the high gain to Earth. And then at that point, we'll spin up our spin-stabilized form of 5 RPM.
You chose Delta IV Heavy for its 2 small spacecraft as opposed to 2 smaller launch vehicles?
Yes.
Because of?
The reason for that is because of our C3. It's at 83.4, which is rather high, and we won't be able to get that from a small launch vehicle by putting one of our vehicles in there. But if there's anything that the Orbits team wants to add on that, please feel free.
Yeah, actually, sorry to correct you, but we could fit on a smaller launch vehicle. The main trade was that they have to launch at the same time. Either they could launch 20 days apart or a year apart. We also didn't have really good numbers on how much it cost for a launch vehicle. That wasn't accessible, but I actually have some rough guesses that we kind of heard rumors of, but maybe that would help drive our decision if we knew that more detailed information.
Slide, please.
At some point, you're going to show us how it all fits in the fairing?
Yes.
Okay, probably.
All right, so here's a little bit of our the images you see here. So during our Earth to Jupiter transit, we are going to be spin stabilized in low power mode. And that means basically we'll be talking to Earth checking in every month, and the probe itself will check in every 9 months. And here you can see the video of our spacecraft being spin stabilized and doing its transfer to Jupiter. So once we're at Jupiter and we have our Jupiter flyby, we will do a system orientation check to make sure that we still have our high gain pointed at Earth and we're still spin stabilized, and then we'll have that unpowered burn. We do, however, have the margin to have a slight burn if need be for any off nominal on our mission. And then after the flyby, we'll do another system check. It's like this. Sorry, what was that?
Jupiter, how many Jupiter radar flyby?
Orbit's team, how many Jupiter radii at flyby?
I forget how many radii, but I think we're about 3 million kilometers.
3 million. You're not getting much out of it.
Yeah, actually, that's all to get there.
Jupiter's gravitational field is so strong that at 3 million kilometers you still get a pretty significant boost in the speed.
Well, I'd like to hear before the data's out, what is the flyby distance?
The periapse radius
Yeah.
is 3 million kilometers.
It is 3 million.
Yeah.
Well, at least you won't have to worry about your own.
Right, and so from Jupiter to Uranus, it's the same from Earth to Jupiter. Essentially, we're going to be spin stabilized and in that low power mode again, giving our system checks. Slide, please. All right, so now we are reaching. Okay, so essentially you saw there the two UPSs reaching Uranus at their separate times, and the orbiters coming in there. You can see the 3 probes dropping over their 5-year period at that point. Slide, please. So once we reach the Uranus sphere of influence, we will be able to check on the probe, warm it up, get it ready for its mission. We will release the probe in its proper orbit, and then we will do that separation burn to get around our Uranus flyby. Slide, please. For the flyby, we need to do a system check, reorient to make sure that helix antenna is pointed properly towards the probe. We'll have our Uranus flyby, and at that point we'll need to rotate the spacecraft again, make sure that the high gain is pointed properly to Earth, and to do our data transfer back at that point. We will have 8-hour increments of our data transfer, and then we will charge for 4 days straight. And then we'll have another 8 hours. We'll do that 5 times, or at least until we have all our data down. At that point, UPS will then continue on its trajectory in space. Next slide, please. Now I would like to introduce Josh Van Schuyt, who will come up here and present the probe architecture and system in full.